All right, welcome. Super excited to be here today to talk through Disney's Foundational Medallion. Let's get started. So we're going to go over a brief overview of the agenda first, what we have in store today. So I'm going to talk about my background a little bit just to give you a little bit of context. We're going to discuss some of the challenges that we're seeing today in the streaming space at Disney, specifically around consistency and flexibility. And then we're going to talk through the solution to those challenges, our net new Foundational Medallion. We're going to take you on a journey. So how did we actually practically implement our Foundational Medallion at Disney scale? We'll talk through some of the benefits that we're seeing from our implementation, and then we're going to wrap things up. So let's dive in. Cool. First, let's start with my story. I've been with Disney for 20 years. I started out at ESPN building software and APIs. I worked on streaming feed ingestion. I've touched just about every kind of database that you can think of. I switched over to the big data space in 2018. I currently lead the core data and services organization. We're responsible for landing all data sets for all of our streaming products at Disney: ESPN+, Hulu, and Disney+. In my spare time, when I'm not answering a bazillion questions from my 8-year-old daughter, you can find me playing USDA tennis or out on the golf course. I also love to travel. My family and I, we ran into Olaf in the heat of summer last year. And good news, he's still intact. I guess he finally optimized his storage format. Cool, let's talk about some of the challenges that we're seeing in Disney's streaming ecosystem. In the streaming space, we have multiple tech stacks from different acquisitions, namely Hulu and BAMTech. The core data platform has many upstream data producers, and it's the core data's job to expose these queryable assets that we ingest. We have many upstream providers that have overlapping dimensionable attributes and key spaces. There's no single source of truth for any of the dimensional attributes. Our downstream consumers desire consistency, and we want to try to solve this once, not all over the place and many teams solving the same problem. We want our core data platform consumers to focus on solving business problems. We also care about our data platform pipeline performance. All of our downstream teams have tight executive reporting SLAs, so we want to keep costs in mind. We also want to provide a single pane of glass for all of our customers. We want key and ID stability over time, and we want to strive for simplicity. So why is solving these problems hard? So Hulu, Disney+, and ESPN+, they're architected slightly differently, and there's many upstream teams. We're talking service providers, change data capture logs, clients, and overlapping attributes between all of them. We're talking massive scale with our data sets that are ingested into our core data lake. We need to support very high volume and a high number of different data sets that we're ingesting. We need to stay cost efficient, and we need to ingest data fast. So we need to support semi-real-time use cases between 1 and 10 minutes. We need to centrally register our assets consistently across all of our data sets, and whatever solution we come up with needs to scale. It can't become a one team bottleneck ingesting all of this data. So we talked through what problems we need to solve, what makes them difficult. Now let's talk through how to get a more consistent environment for our downstream consumers. First, let's do a super quick review of the medallion architecture. Our bronze layer contains raw data. It's generally append only. There's different serialization types. Our silver layer is typically cleaned, standardized, enriched, delta and parquet format. And our gold and aggregate summarized silver layer is analytics ready. All right, let's unveil the solution to the problems that we just discussed. We are going to build a new framework that mints a new foundational medallion. It's a configuration-based surrogate key and dimensional modeling system. So where does this new medallion fit in? Our new foundational medallion fits right in the middle between bronze and silver. It's a mechanical, configuration-based application, and not a ton of business context is needed to produce this new foundational layer. Everyone downstream benefits. So let's move on to a key technical design decision. So how are we going to mint this new foundational medallion with adding a new set of surrogate keys and sending data out for dimensionalization? Are we going to go with a centralized model or a decentralized model? Let's talk through the pros and cons of each. With a decentralized approach, a foundational job that's ingesting data sends out keys and metadata to our dimensional management service. We probably go with a deterministic key creation that's decentralized, such as a hash. Our keys are typically larger in size, and it's easier to implement this type of design. It's asynchronous, you basically fire and forget. It's also hard to handle collisions. We have to handle those in the dimension tables after the fact. Let's move on to a centralized approach. Centralized approach is harder to implement, but you get the benefit of numeric keys, which reduces storage size, increases performance across the board with joins and range queries, and the keys are human readable, so teams can pass them around. What did we end up going with? We chose a centralized approach. The benefits are too alluring of numeric, consistent base keys. We decided that even though it's technically challenging to implement, to do or do not, there is no try. So let's expand on the challenges of a centralized implementation. Cool, so we have many foundational ingestion jobs building our foundational medallion, and we have many different data sets. Each data set has many overlapping dimensional attributes. There's race conditions to handle in our dimensional and surrogate key generation system. In our centralized key system, we're going to create monotonically increasing numerical IDs. We're going to funnel all of our creation requests into a centralized location, and performance is key. So we don't want to be a bottleneck in data being ingested. We need to evaluate a trade-off of latency versus data completeness. We'll talk about that in a minute. We also want to be cost conscientious. There's many ways to create surrogate keys, and at Disney scale, billions of calls to APIs and dealing with locking mechanisms is definitely not financially reasonable. So how'd we do it? Let's walk you through. But first, what tech stack are we using? So we're relying on Delta identity columns for a key component of our dimensional system. We're using Unity Catalog to register all of our assets, foundational layer, as well as bronze, silver, and gold. We're relying on liquid clustering and Photon for performance improvements, specifically in merging into our dimensional tables very efficiently. We're using uniform format for ease of integration with data warehouse engines, and we're relying on the DBR runtime for our foundational processing, which is, utilizes the disk cache very well. We're deployed in AWS using Spark, Scala, Airflow, and Datadog. So next, let's walk you through what we want to do at a high level. Our foundational processing, so what is it actually doing? For all of the dimensional attributes, we are adding consistent keys and sending out those attributes to our dimensional system. We're writing out our foundational tier that has the consistent keys added. And each data source has one or many dimensional type attributes. This could result in many joins in our foundational processing. There's a lot of performance considerations we had to think through here and how to do this efficiently. There's also performance considerations for creating our surrogate keys and dimensional tables. When sending an attribute to get created, we need to think through our key creation process. Which version of the key gets there first? Which version of the dimension gets there first? And we need to design for a centralized key creation. Should we hold up all of our data going through our bronze foundational silver layer if no data is found in our dimensional table. Where does our foundational processing fit into our overall architecture? So let's walk you through the reference architecture for our foundational medallion. Over to the left, you're going to see many sources of data. Streaming and batch-based sources were primarily AWS-based. A lot of different serialization formats like Avro, CSV, Protobuf, JSON. We have a standardized landing service for our bronze layer that lands data wrapped into a Delta format. It's raw data, not manipulated. Our new foundational tier is configuration-based to scale to all the teams in our environment and consumes from our bronze layer via Spark streaming. The foundational processing tier joins to the dimensional tables, adding the consistent surrogate keys to our datasets, and then sends attributes not found out for creation. We then produce a new foundational medallion that everyone can benefit from downstream. So let's double-click on our foundational processing. Cool. Our foundational Spark service joins to one or many dimensional tables. We're talking billions of records joining to millions of records in our dimensional attribute entries. We get the surrogate key and we add it to the record. There are multiple attribute types per record, so we need to do this many times. We send those attributes out to get created and add to our dimensional tables if they don't exist. We had an architecture design decision to make here and weigh the trade-offs between latency and data completeness in our foundational layer. We ended up choosing an eventually consistent approach, a big data DLQ implementation using Delta format. Records that have missing dimensional entries are quarantined and wait for creation. A high percentage of join hits across our dimensional attributes allows us to do this. So 98 to 99% of the data makes it through with no misses. The DLQ system waits on 1 to 2% of the keys and dimensional attributes to get created. Our DLQ processor joins and inserts to the foundational medallion. DLQ records typically arrive about 1 to 2 minutes late. Observability is key in our foundational and DLQ processors. They're both monitored for latency. So dimensional attribute creation performance is also critical to keep the overall latency low. But how? Let's talk through it. So our dimensional streaming ingest, again, we want to create dimensional entries as fast as we possibly can. There's many iterations of design here and performance tuning. This is where we're using Photon and taking advantage of some of the capabilities there. We're merging records into a dimensional table that may have billions of entries in the dimension. We're funneling requests that are coming in into a staging table, a DIM staging table. And we do that to serialize the creation so we can have monotonically increasing IDs. We also had to solve for a small file problem, as a lot of small requests come in for a few dimensional attributes at a time. We're constantly inserting, sometimes in small micro batches, and we need to optimize those files every so often to allow our foundational processing to join efficiently. We also built out a custom-based autoscaler that works with Spark streaming. And it's custom in-house built. It's triggered off of Spark metrics from our dimensional ingest service, and it's based on number of files to process. So if we get a lag, then we'll scale up and add nodes. We're using AWS Lambda, and we call into the Databricks API to scale up our Spark streaming jobs and also scale down. This helps us deal with bursts and backfills and all sorts of things. Let's double click on our foundational processing jobs and what we're doing there. So with each micro batch coming in, there are multiple joins that we have to do for each dimensional attribute. So we find our missing dimensional entries first, doing an anti-join, and then we send those out for creation. Next, we do the actual join to go pull the surrogate keys, And we do this multiple times per record because each record can have multiple attributes. There's many iterations of performance tuning we had to go through here. We started with multiple shuffle-based joins, which that was a complete non-starter. Many iterations later, we broadcast each micro batch coming in. We had to tune the Spark parameters and batch sizes, and each micro batch fits in memory. Dimensional tables are distributed in a data frame on each one of the workers, and that allows us a super high cache hit ratio, which we barely need to go back to source for. We applied the same in-house autoscaler to our foundational processor, and we triggered off files waiting to be processed. Let's talk through some of the results that we've been seeing. We've seen a substantial increase on downstream joins, 3x, resulting in lower downstream costs. Teams are now able to lower their SLA times, and we have happy execs. We're providing a more flexible environment for our upstream data producers and a more consistent, stable environment for our downstream consumers. We built out a solid foundation for ML and analytics use cases with numeric keys everywhere. We improved our downstream internal customer satisfaction, and now teams can focus on solving business problems rather than trying to create dimensional tables. We built a solid foundational medallion to build insights and data products from downstream. Cool. So let's wrap it up. Let's tie it all together. So we explained what problems we wanted to solve. We have many data sets, overlapping information, lack of consistency. We have many producing and consuming teams. We wanted to increase the downstream performance at a platform scale and really have a big impact on our platform. We wanted to simplify our environment and allow downstream teams to focus on solving true business problems. We also wanted to prevent teams from solving overlapping problems by handling the dimensionalization altogether. We then talked through how we implemented our foundational medallion layer to solve these problems. We focused on some of the Spark techniques that we used to meet our latency SLAs. We also walked through our custom DLQ-based approach to offset consistency versus timeliness. And then we walked through some of the amazing results that we're seeing. So thank you all for coming out. I really appreciate it. And come join our team. We're hiring.